Hello, I'm Sankaran from Northwestern University and Argonne National Laboratory.
And I'm Bill Miller from Northwestern University. This afternoon, Raj and I will discuss new environmental sensors deployed at Emiquon and how they can be used to increase our understanding of this complex ecosystem.
Thank you, Bill. Good afternoon, everyone. The work we are sharing today is strongly rooted in the collaborative efforts of numerous individuals from diverse institutions, all contributing to the SAGE project. SAGE is a project funded by the National Science Foundation to design and build a new kind of national scale, reusable cyber infrastructure to enable AI at the edge. The project is led by Northwestern University and leverages open source hardware and software tools developed by Argonne National Laboratory. So here we go. Well, observation is foundational to science. In the not so distant past, scientific observations were conducted using modest, uncomplicated instruments. We meticulously noted our observations and subsequently engaged in the mathematical analysis and predictive modeling based on our findings. Before the age of computers, humans served as primary computers. That is right, we were the computers. And today, we employ extensive arrays of multi-million dollar observation platforms that extend across vast distances, both on Earth and into outer space. This is made possible by remarkable advancements in sensing technology, digital electronics, and computing over the past few decades. The advent of digital computers has completely transformed how we tackle tasks that were previously performed manually by humans. What you're seeing here is a land observation site managed by the National Ecological Observatory Network, NEON, providing valuable ecological data from various locations across the continent. At the heart of this site stands a NEON sensor tower, while nearby sits the instrument hut, a prime location for integrating computers and efficiently processing the vast amounts of data generated by the sensors at the highest resolution. The key here is that the data can be processed at the highest resolution very close to the sensor, and we can extract valuable insights into ecological patterns and processes. This new paradigm of computing is what we call edge computing. It refers to the practice of processing data closer to the source of generation rather than relying solely on centralized data centers or cloud computing resources. In edge computing, data processing and storage occur near the edge of the network, typically at or near the devices or sensors that collect the data. In fact, the entire spectrum of computing, ranging from edge computing to high performance computing, is well suited for a seamless cycle of computing and control as shown here. Analyzing data at the edge can initiate extensive HPC simulations, which in return can influence the sensing and analysis processes at the edge. So, what are the practical applications of edge computing? What can we achieve with it? Well, by closely examining images, video, audio recordings, LiDAR data, and other sensor data at the highest level of detail near the source in a manner that preserves privacy and conserves bandwidth, we can explore a wide range of phenomena. This includes studying plant species, bird calls, pedestrian traffic patterns, wildlife behavior, wildfires, flooding, and more. By integrating the state of the art AI techniques, we can conduct measurements, detect anomalies, and implement control mechanisms at the edge. These analyses can generate real-time insights and understanding, leading to immediate alerts and integration into analysis pipelines. Through the SAGE project's adoption of industry standard methods and tools, the barriers to conducting these edge analyses are greatly lowered. In fact, a single image can be examined for various features or events depending on the specific application or scenario. For instance, a camera image capturing a busy street could be analyzed for standing water post rainfall, traffic flow during flood or snow conditions, or to comprehend the pedestrian traffic interactions. These analyses can be conducted simultaneously or periodically according to the scientific requirements, all facilitated by software. We call this software-defined sensing, where the data we gather is influenced by both the instrument or the sensor and the software used to interpret its output. The SAGE platform offers field-ready nodes that can easily connect with sensors, actuators, and instruments through a wide range of wired and wireless connectivity options. Subsequently, we can execute analysis applications on the edge nodes, enabling real-time control over the sensors and their parameters. By combining these elements, we can establish an internet-connected AI at the edge platform capable of analyzing and managing sophisticated sensors and instruments through these edge applications. Through the years, researchers and students have developed numerous edge applications. The table on this slide showcases a diverse array of these applications, detailing the AML methodologies employed and the breadth of their deployment. Taking inspiration from application marketplaces such as Apple's App Store and Android's Play Store, the Sage Cyber Infrastructure also features an online collection of readily deployable applications. These applications, contributed by students and researchers, come with open source code and data whenever feasible, enabling them to be customized and improved for other purposes or to serve as a foundation for entirely new applications. Later in the presentation, Bill will showcase some of these applications. So where are these applications deployed? What exactly are these Sage nodes? Well, Sage offers two types of nodes. First, there are the wild Sage nodes. These are designed for field use, meaning they can be deployed outdoors in various weather conditions, including rain, heat, cold, and snow. The other type is the Sage blades, better suited for deployment in telecom grade enclosures or the neon huts that we saw earlier. These enclosures or huts are designed to keep water out but may not offer the same level of temperature control as a dedicated server room or office environment. For our Intelligent Environmental Sensing initiative at the TNC Emiquon Preserve, we have deployed two wild sage nodes equipped with a range of sensors. In this illustration, we see a standard wild sage node featuring two cameras, one facing upward towards the sky and another facing downward, observing the ground. Each node is outfitted with environmental sensors, including those for temperature, pressure, humidity, and precipitation. Additionally, the Sage nodes boast an omnidirectional microphone and house 2 to 3 NVIDIA Xavier GPUs and Raspberry Pi computers for executing edge applications that we discussed earlier. They offer multiple internet connectivity options such as Wi-Fi, cellular, and Ethernet, with select nodes out in the field also using Starlink satellite connectivity. Beyond these sensors, the nodes feature interfaces for adding supplementary sensors, including USB and Ethernet. Moreover, nodes can be expanded with LoRaWAN, a low bandwidth, long range wireless connectivity option, enabling the integration of various sensors within a 1 to 2 mile radius of a node. Bill will describe a few of these sensors later in the talk. At Emiquon, each of the two deployed nodes is equipped with additional sensors. These include the Vaisla weather station, Met1 air quality sensor, Mobotics thermal camera on a pan tilt pedestal, and a continuous PTZ RGB camera. These sensors offer the capability to monitor various parameters, adjust camera angles in real time to track interesting phenomena, and notably, through Sage, utilize triggers from one sensor to influence the data or steering of another sensor. This interconnectedness allows sensor data to trigger actions in other sensors or computing systems, enabling the synthesis of new real-time insights and observations. As previously mentioned, two nodes with a suite of sensors have been deployed at Emiquon. These nodes are mounted on quick deploy towers designed to minimize ground disturbance. They are self-supporting structures that can be easily disassembled and relocated to a different site. The first node is situated near the ostrich barn, while the second node is positioned near the entrance to the visitor use area. Here are some images showcasing the towers and the views captured by the cameras. Bill will provide further details on these images later in the talk. The visitor use area node is what we call off-the-grid node. Unlike the ostrich barn node, which is line powered through 110-volt wall plug, like in your home, this node is powered using solar panels and DC power supply. Here you can see some of the construction and deployment activities carried out in rain, shade, and shine with large cranes, tractors, and hand tools. Before diving into the specifics of the Emiquon deployment, let's briefly discuss how Sage and these systems can be utilized. The diagram here illustrates several entry points for users represented by blue arrows. First, all users can utilize the data provided by node applications. Next, advanced users can participate in the decision-making process regarding which applications to run, when and how to run them, and what data to collect for analysis or use. Finally, experts can explore new cyberinfrastructure techniques, train new AML models, and develop applications for their own use and for the benefit of the community. The strength of the Sage's application sharing approach lies in the ability of users to benefit from applications developed by others while also contributing their own, thereby creating a collective benefit greater than the sum of its parts. And now Bill will discuss some of the examples of data collection and processing at Emiquon. Please take it away, Bill.
Now I'd like to share some images from the Sage nodes. The fisheye camera image on the left extends to the horizon and captures clouds and shows the lightning rod. The pan-tilt zoom camera, or PTZ camera, on the right shows the entrance to the visitor use area and the fork in the road leading to the boat ramp to the right and to the observation and interpretive areas to the left. I'll come back later to discuss how we can use these images. The Mobotics camera produces visual and thermal images. The red dotted box on the left shows the approximate area within the visual image that's captured in the thermal image to the right. Warmer colors represent warmer temperatures. You can see in the image on the right that bare ground is the hottest, sort of a whitish pink, and that vegetated areas, either in the foreground, within the wetland, or in the tree line along the horizon, stand out from the cooler water and air. You can also note that clouds are warmer than the open sky and that shallow water is warmer than deeper water. In this set of images, the large bird circled with a white dotted line in the image on the left appears to be an eagle in flight, as shown by the blow-up image in the title line. This bird also shows up circled in the thermal image. Based on these results, it should be easy to identify flocks of birds rafting on the wetland at night. The image from the PTZ camera on the pole at the ostrich barn, shown on the left, captures grassland down to the highway and also provides a view of the wetland and the tree line along the river. These images were taken by the robotics camera at the ostrich barn. Snow on the ground in the image to the left shows up as dark blue in the thermal image on the right. In contrast, the brush shows up as sort of a greenish yellow in the thermal image. Even on this cloudy day, we can make out the wetland and the tree line in the thermal image on the right. The robotics scan algorithm takes three sets of images. First, mostly focused on the ground. Second, focused at the horizon line. And third, mostly the sky. It also provides a temperature scale for the thermal image. The thermal images on the right only include the area below the building that shows up in the top of the left image for the visual picture. You can note on the right the relatively narrow temperature range going from about 1 degree to 16 degrees for this ground-based image. You can also note that sort of the hot white pink in the upper image shows up as an orangey red in the lower image. In this horizon view, we clearly see the building just below the horizon in the thermal image to the right. We can also see the wetland and the tree line as distinct bands. Note the sky temperature decreases as you move above the horizon. Also note that the very wide temperature range going from -60 to +60 degrees makes the ground look more uniform in temperature. In this sky view, we appear to catch the top of the tree line in the thermal image, which clearly shows the temperature gradient within the sky. This temperature gradient is less apparent in the temperature scale image because of the very wide range ranging from -80 to +80 degrees C. As Raj noted, many apps have been created for processing the camera images and sound patterns on the Sage nodes. The performance of these apps is still being improved, and more apps are under development. The apps shown on this slide with red dots have been implemented on the Emiquon nodes, and I'll illustrate these with a few examples. The Nature Conservancy is interested in learning more about how people use the Emiquon preserve. For example, how many people launch boats each day, or how many cars proceed to the visitor and information areas to the left. The Object Counter app processes images from the pan-tilt zoom camera on the Sage node. The images in this slide show two of the objects that were detected by the app. Although, as you can see, the app is still somewhat erratic now. For example, it missed the boat trailer on the right and missed the truck and the backhoe on the left. These images, especially those shown in the blow-ups at the bottom, illustrate the potential of this app. I should note that these camera images, as well as any other camera images from the Sage node, are only accessible by people who have completed the Sage Protected Data Use Agreement for the Emiquon nodes. However, the actual number of vehicles that are detected would be generally available to the public, along with things like weather data and air quality data. Images from the top camera can be used to quantify the extent of cloud cover, as shown in the graph, the top graph on this slide. The regions with horizontal lines close to fractional coverage of 1 represent night when you can't detect the cloud cover. The top camera can also be used to detect solar irradiance, and this is shown in the bottom graph for the same time period. You can see that the peak solar radiance for this period in late February was about 450 watts per meter squared. As you would expect, times with low cloud cover correspond to high solar radiance and vice versa. You can especially contrast the second day in the plots versus the fourth day. You might also notice that even when solar radiance is quite low, say near dawn and dusk, it's possible for the camera to detect fractional cloud cover. The Avian Diversity Monitoring app incorporates the Cornell Merlin app for bird identification. The thousands of species included makes the display very cluttered. This slide shows results from March 6 to 11. Each dot shows the time and relative certainty for species attribution. As expected, most activity takes place between dawn and dusk. The most prevalent bird identified with high certainty is the killdeer, which should not be surprising if you've been to Emiquon. However, the American woodcock was also frequently detected. The great horned owl was detected several times on March 10th in the early morning, while a loggerhead shrike was detected on March 7th. The MET1 air quality sensor detects particulate matter between 0.5 to 10 microns. This slide shows higher levels of particulates for about 10 hours, going from late afternoon on November 8th to early morning on November 9th. As Raj noted, power requirements of SAGE nodes demand that they either be connected to line power or a large solar array. However, these SAGE nodes can also be used to collect and process data from low-power sensors located up to a mile away using LoRaWAN wireless technology. This slide shows a variety of LoRaWAN-enabled sensors that we're using for projects in the Chicago area as well as in northern Wisconsin. Many of these sensors are likely to be useful at Emiquon, for example, water level, temperature, and conductivity. Signals from the sensors can also be used to trigger actions by the SAGE node. For example, if high wave height is detected at a particular sensor, the SAGE node could focus the pan-tilt zoom camera on that area to get a better idea of what's happening.
Thank you, Bill, for your insightful overview of the sensing and inference activities at Emiquon. As we conclude our discussion, I would like to highlight two key points. First, beyond the scope of Emiquon, what truly excites us is that these two nodes are a part of a larger network of SAGE nodes worldwide. Beyond what's visible on this map, numerous projects deploy SAGE nodes, making data accessible to the community. Secondly, the sensor knowledge, interfaces, algorithms, and analysis codes used in these nodes are typically open source, providing opportunities for collaboration and exploration. To learn more, please visit the SAGE website. And to take a moment to appreciate the research possibilities enabled by a network like this, I have two examples to share with you. In December 2021, a volcanic eruption began on the Tonga Hunga Hapai, a submarine volcano in the Tongan archipelago in the southern Pacific Ocean. The eruption reached a very large and powerful climax nearly 4 weeks later on the 15th of January 2022. Described by scientists as a magma hammer, the volcano at its height produced a series of 4 underwater thrusts, displacing about 10 cubic kilometers of rock, ash, and sediment, and generated the largest atmospheric explosion recorded by modern instrumentation. And we saw it on our system. We saw it using inexpensive $5 sensors across the continental US on a network that was sampling data at 2 samples per minute and that was in its infancy with hardly 10 nodes deployed at that point in time. This is the power of a network like SAGE. We saw waves go past not once, but 3 times, and this only begs the question, what could we as a community study if we were looking for events attentively? And this year, we had severe thunderstorms in northwestern Illinois on 27th of Feb. Various SAGE sensor nodes and nodes from other projects capture the swift temperature drop as the system approached during the evening. The sharp declines in temperature depicted with two descending lines there represent the nodes at Emiquon, indicating a faster cooling rate in comparison to the greater Chicago area. Such detailed and local analysis of events can be achieved solely through the networks like these. With that, we wrap up our presentation. First, thank you for offering us a chance to speak at the Emiquon Symposium. We also sincerely value the ongoing support and collaboration from the Emiquon staff throughout the years. None of this would have been possible without your contributions. Thank you. Finally, our thanks for your time and hope to collaborate with many more of you in the coming times. Thanks much.